Hi everyone, welcome to the next video. This is an introduction to related rates. You can see the objectives listed here. Related rates come directly out of using implicit differentiation and also the idea of a derivative as a rate of change. Related rates problems use geometric formulas. The formulas for the volume, perimeter, area of all the different basic shapes: spheres, cones, cylinders, rectangles, triangles, circles, all of those from geometry. So I have a handout for those if you have forgotten some of them, but we're going to use a few of them in this video. On the next couple of screens, there'll be some classic problems using related rates. So for instance, inflating a spherical object. You can see somebody blowing up a balloon or a ball. And also this motion of a ladder against a wall, right? You could say that the ladder was moving this way, and then this is moving this way as well. So moving down the wall, moving away from the wall, towards the wall, of course there's going to be a limit as to how far you can do that. Reducing an object in size, a spherical object, for instance a jawbreaker or a lollipop of some kind. Creating a cone-shaped pile of gravel, right? It's going to be creating that shape at a particular rate. The height of the cone is going to be changing, the radius of the cone is going to be changing, and also this length here, the slant height of a cone is going to be changing. So on the next few problems, what I'd like to do is show you how to implicitly differentiate these formulas with respect to time. These are some of the classic formulas. The first two have to do with a sphere. We have the surface area and the volume of a sphere. One interesting thing, that if you took the derivative of the volume of a sphere, you get the surface area. So what we're going to do is we're going to take the derivative of the area. We're just going to take the derivative of both sides with respect to t. So we're taking the derivative of the area, and that's going to equal 8 pi r and then dr dt, because we're taking both derivatives with respect to time. And so dA dt would be the rate at which the area, the surface area, is changing. So this is a rate that the surface area is changing. All right, and then dr dt would then, of course, be the rate at which the radius is changing. So you'll often get a problem that will talk about the changing of, the radius is changing at a certain rate, find the rate at which the area is changing. Okay, if we were to do the volume, we would do the same thing. dV dt is equal to 4 pi r squared, right, because the derivative of the volume is the surface area, and then dr dt. So every time you take the derivative of a variable, you're going to take the derivative with respect to time. And so dV dt is, once again, the rate of change. So it's the rate at which the volume is changing. And then, of course, dr dt is the rate at which the radius, so the same thing that we had here, the rate at which the radius is changing. It's a rate, though. That's the important thing. So the next one that they have on here talks about a triangle. And the hypotenuse is C, and then you would have A and B. And then C is a constant. And where you would see this is a ladder leaning against a wall. So B might be the wall, this might be the ladder. All right, well, a ladder doesn't change size. in the problem. It's going to be 25 feet, 26 feet all the time. And if it's not changing, then dc dt will be the derivative of a constant, which is 0 every time. So what they've done here, the Pythagorean theorem is c squared equals a squared plus b squared. So they have solved for a. And then you would take the derivative. Well, you can see here that this would be a chain rule, right? It would be something to the 1/2 power, and then you have a bunch of the fractions that way. I think a more elegant way to do this problem, no matter how you do it, is set it up as a Pythagorean theorem. So most people would set it up a squared plus b squared equals c squared. I actually like to use x, y, and z because this is the x direction on a coordinate graph, this is the y direction, and then c, you could use h. Sometimes they'll use h. But in any way, if I took the derivative of this, I would have 2 dA dt, I'm sorry, 2a. I got too many buttons to hit. All right, 2a dA dt plus 2b dB dt equals 2c dc dt. All right, and so then what you realize is this is going to go to 0. And then if you needed to find dA dt or dB dt, once you plugged in the information, you would be able to find it just as easily as setting it up this way. So I think this is a more elegant way, and that's what we're going to use in class. All right, so the next problem we have is the volume of a cylinder, V equals pi r squared h, where r is a constant. So in this particular one, the radius does not change, but the height does of a cylinder. Remember what a cylinder looks like. All right, so the radius would be here, and the height would be here. And so once again, I'm going to do dV dt. Now, if r were not a constant, we would be using the product rule. But because it is, I'm going to have the constant is pi r squared, so I'm not going to be taking the derivative of that, which I'm not used to. And then the derivative of h is just 1 dH dt. So once again, we have a change in volume and a change in height. If we were taking all of them, it would be a lot more complicated. Oftentimes in this type of problem, we would set up a ratio of radius to height, and then a lot of times what's happening is you have water being poured in. So there's a change in volume anytime you pour water, or water goes into a solid figure or into a figure or coming out of it. That would be a rate of volume. Right? And so then the depth of the water for a cylinder, the depth of the water would be the change in h. And so oftentimes that's what you're finding is the depth of the water. Now, if you look at the next one is a right triangle, and they're using trig functions. Now, this particular one uses cosine, but I've also seen tangents, especially if you had a value here. And oftentimes they'll call this direction, this will be x, this direction will be y. And then this looks like a ladder or something that doesn't change. So if we took the derivative of this, if you take the derivative of the left side, you would get negative sine theta equals, and then the derivative of the other side, d theta dt, almost forgot, but I didn't. All right, and then equals 1/15 dx dt. And so you can see d theta dt is going to be the rate at which the angle, so at the rate at which the angle is changing. And the angle will be in radians. And radians, this is kind of important. Anytime you have a trig function in calculus, you're using radians. And then dx dt is going to be the rate at which that side is changing. All right, volume of a cone. Now notice that the volume of the cone, there's no constant in here. So once again, this is going to be a product rule. And also, the other thing I wanted you to notice is that a cone is a third of a cylinder. So a cone is a third of a cylinder. That is why those formulas are so similar. All right, so notice that 1/3 pi is a constant. So oftentimes what I will do is leave the constant on the outside and then take the product rule of what's left. So you would have first times derivative of the second plus the second times the derivative of the first. And so you would want to tidy this up a little bit. Multiply through, I would probably write this as 2RH instead. But pretty much you would have to be given all of this information except for one variable or one dV/dt. Say, for instance, you were trying to find that, then somehow you would have to be given the radius, height, and the two rates of change. So on the next one, we'll do an example. So the radius of a sphere, so there's our formula. It says the radius is increasing. That tells me that the rate's going to be positive at a rate of 3 inches per minute. Inches per minute tells me it is a rate of change. Okay, so we're going to divide these problems. If you'll set it up this way, this method has really served me well because it gives us a way to determine what we've been given, what we need to find, what is the constant, or what is happening at that particular instant, and then an equation. So here's what we want to do. We want to write down what's given. Well, what's given is that we have a sphere and that the radius of the sphere is increasing. So dr dt has a rate of 3 inches per minute. All right? And I want to find the change of rate of volume, the rate of change of volume, when the radius, at the instant when the radius is 9 inches. All right? So since we're looking for volume, we want the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. We want to take the derivative, so dV/dt equals 4, remember 4 pi r squared dr dt, and then we're solving for dV/dt, and so we have 4 pi r squared, r is 9, and then dr dt is 3. So we're going to end up with 81 times 4 times 3 times pi, which will be 972 pi. And then this is a change in volume. Remember, volume is cubed. So this will be inches cubed per minute. If you had a change in area, it'd be inches squared. If it's just a side changing, it's inches. So dV/dt, the change in volume, when the radius is changing at 3 inches per minute and the radius is 9 in that instant, would be this answer. So we're going to do tons and tons of these. So be prepared to think about what is changing, what is staying the same, and I think you're going to find these to be pretty fun. But I will see you in class.